Thank you. Yeah, hi, I'm Chris. I'm a software engineer at Google. And after working on gVisor, I kind of moved to another crazy Go project. Um, we've now started writing some firmware in Go. But before I get to that, I'm going to tell you a little bit about what firmware is and some pre-knowledge, I would say, before I actually go into the Go project. Firmware is essentially two things. It's the first software that actually runs on your machine when you turn it on. First in, I'm going to put that in air quotes, but like the first actually programmable software. Is usually stored in a flash chip somewhere on your motherboard. Something with like a size of maybe 16 to 32 megabytes at most. And firmware is also a bootloader that loads, other stuff like Grub or Windows on your machine. Firmware usually does two things, right? One, it initializes hardware, like turn on RAM, turn on other random devices and stuff. That's not really important to us here at the moment. The second one is that it also acts as a bootloader, like I said, for Grub or Windows and stuff. So it has to know how to read things from disk. Sometimes it knows how to like download things from the network, like in PXE booting, stuff like that. On x86, like on most servers and workstations and laptops that you buy, the firmware you get is UEFI. And this picture, you don't actually have to understand this. I put this here for you to see that it's complicated, and for you to see that there's like some keywords, like there's drivers involved, there's like a scheduler involved, there's like random applications you can run. You can actually run kind of arbitrary PE32 executables in UEFI. And if you squint at this for long enough, you'll notice that like it kind of looks like an operating system, right? Your firmware looks like an operating system, and it has millions of lines of code. And we're going to use that observation in a second. And I'm going to skip the rant that I usually do about UEFI at this point and tell you that it's all closed source. It's the most trusted piece of code on your machine because it's the first thing that turns on and actually has control over it. But it's the one with the least visibility, right? You can basically look at almost none of it. There are some open source reference implementations, but you can't use those to build a valid UEFI firmware for literally any machine on the x86 planet, except for some virtual machines. So it's all based on some proprietary information that isn't available to you. So you have very little visibility, but you actually have a huge attack surface, given that it's multiple millions of lines of code that are involved here. And the problem that we kind of started looking at is that you don't really own your platform if you don't have control over the first thing that runs on the machine, since it controls what's going to run next. So this project actually takes Linux and places it in UEFI as a UEFI module. And that's based on two observations. A, Linux doesn't actually need firmware to initialize much. Linux knows how to talk to most devices if they haven't been initialized at all. So all those like disk drivers and network drivers and all that random stuff that's in firmware, you can take out because Linux already has it. And Linux likely has a better implementation than firmware does, right? You can also already compile a Linux kernel as an EFI PE32 executable. Kind of gets like put in this little box with like maybe a little bit of boilerplate code around it. So I can actually take a random UEFI module, replace it with Linux, and replace or remove a whole bunch of UEFI modules that have drivers for stuff and other random things. So the relevant part here is that, as opposed to UEFI, while some people also don't like Linux, and Linux has its own set of problems, as we, I think, probably all have heard of, Linux is open. I can actually compile Linux for myself and reproduce what's been built for my machine. I can actually measure Linux. And if I look at the number of contributors to the UEFI reference implementation, which is somewhere around like 190 at this point on GitHub, and I look at Linuxes, which at this point GitHub has stopped counting, and there's been a lot more eyes on Linux and a lot more security fixes for Linux than there have been for UEFI. The other observation you can make is that now all your kernel engineers and sysadmins and people that know stuff about Linux actually know stuff about firmware and may know how to administrate that kind of environment. You don't have to learn something completely new to deal with firmware. A nice side effect is that on some platforms, we've actually seen major boot time reductions, something like 8 minutes to 20 seconds. That's usually a nice side effect of this. But let's get to the Go part of this. And that is, if you put Linux in firmware, you need to have something in user space. Linux is usually compiled with something called an initramfs. An initramfs is basically an archive of files. Think a tarball. That initramfs gets unpacked and put in like a tempfs RAM file system, like an in-memory file system. And Linux will look at the /init file in that initramfs and try to run it as the first process in user space. Right? That's process ID 1. Usually, because of size constraints, these like initramfs are small, and they contain a bunch of like tiny C tools, like BusyBox, if you've ever done any like embedded development or stuff like that. But you know, it's 2019, and most of us on this project are pretty sick of writing C and Bash. So what we've actually done is we've written a whole bunch of Linux-like userland tools in Go. The project is called uroot. And I should say that as the LinuxBoot project, we try not to force you to use anything. Like, we provide you with tools. You can put things together the way you want. So if you want to use LinuxBoot and use a bunch of C tools that already exist, like petitboot or systemdboot or BusyBox or whatever, like, we'll help you do that too. But the tools that we're actually developing are in uroot in Go. So, you know, this is also based on the observation that we now have the full tool set of any Linux application at our fingertips. It just has to be small enough. So about that, you may know that Go binaries are not usually actually small. You know, like a normal hello world comes out to maybe 12 megabytes, I believe, something like that. But we've come to the point where we can compress a Go initramfs down to 3 to 5 megabytes of space. And that's usually about as much space as we have on UEFI platforms where we put Linux in. So this contains like a suite of 30 plus tools that are your usual Linux stuff, like cat, dd, ls, cp, all that stuff. They're usually basic re-implementations. We're not trying to go for full feature compatibility. They're just supposed to be what you need for debugging and like small environments like this. So how do you make it fit? The answer is, if you really need to make it fit, it can only be one binary, right? I have 30 plus commands, but I need to take them all and combine them into one. And to do that, you know, imagine like a huge main function that looks at the first argument of what's being called and says, you know, if it's ls, I run ls main. If it's cp, I run cp main. If it's dd, I run dd main. I think you get that picture. But we also don't want you to have to write the tools against uroot. They should be just like any other Go command, package main with normal main and init functions, so that you can choose to like, hey, I want these 5 tools to be compiled together into initramfs, or I want all 30 of them. Because on some platforms, I don't have space for all 30. I need to get an initramfs that's only 3 megs compressed. So what we've actually done is write tools that do a source-to-source transformation on the commands. Basically, we take the commands and we rewrite them as packages. In its most basic version, that's like take main and rename it to uppercase exported main, something you can call from the outside, but that doesn't automatically get run. And rename the package name to the tool name based on the directory, right? So if I have like a command ls with a package main in it, I'll rename package main to package ls. You'll start seeing that kind of breaks apart. Just renaming things is not enough, because you can have multiple init functions, but you can't have multiple exported init functions, right? So I need to start like exporting them and numbering them. So init becomes init0. The other thing is that global variables are going to start conflicting with each other, right? If I run dd, I don't want to see cp's help message because cp's init, had a flag that defined the help. And if you look at the spec, global variables are actually just like inits, except it's syntactic sugar, right? So if you move that that assignment to an init function, and you just leave the declaration, you should be good. That means to do this, you also have to do type checking, because now you got to figure out what's the return type of flag.string to actually figure out what the type of var name is that's usually inferred. So that's another complication here. Now it's not just looking at the source and rewriting it. You actually have to parse it all and figure out what's where and how. But Go already has tools for that in the standard library. The other thing to notice here is in this example, the order of the inits matters, right? Because I'm actually using the name in the other init, init1 has to run before init0. The Go standard library will also tell you the init order that things are supposed to be run in. So we end up writing like an actual init function that calls them in the order that they should be called in, according to the Go runtime. And then the real init registers the command and its exported init and main functions in like a global map of commands. What's left to do then is to write a main function that imports it all. Right? You do this for all commands that you want as packages. You import them with an underscore like this, since they use init to register themselves. And then this bb.run thing actually just looks at the map of things and says, if it's ls, I'll run the ls registered init and main, stuff like that. Now this actually builds pretty quickly. So I'm going to show you, hopefully, if internet works. How to make one of these. So all I'm specifying here are the Go import paths of two different commands. And because we use GoPath to figure out where these are, you can actually do globs and nice things like the brackets, like that. You don't have to spell them all out. This is going to take maybe 15, 20 seconds. Oh, that was pretty quick, actually. And to get the first argument of these to be the name of the binary you need it to be, you make a symlink, like from CP to BB. So now when I run this, it's /CP. It runs the BusyBox binary that I built, but the first arg is CP. And now if I do ls, so this is actually the BusyBox ls, just to compare with the real ls. It's a little bit simpler. So make BB will compile you a small binary like this. And actually, I totally lied, because these two commands together are only a 2.4 megabyte binary. And like I said, because we don't want you to have to write commands against uroot, this should work with any Go command, right? So I should be able to take a random GitHub repo Go command and pass it to make BB like this. Like, for example, the gosh Go shell that you could use. Now, the uroot command builds a BusyBox and embeds it in an initramfs. So if I, instead of using make BB, use uroot build BB, and I'm going to just build them all. This is going to take a little bit longer. I'm going to get all of the commands in one initramfs. That ends up being something like 17 megabytes. Right. If I compress that, oh, I've already done this before. It should come out to something like 5 megs. Let's take a look. 4.7, okay. So I can take this now and, okay, run it in QEMU. Sorry, the command line cuts off, but there's a dash kernel with a kernel that I built before and a dash initrd that passes this initramfs. Oh, great, because I compressed it, it's gone. That was easier than fixing the command line. So this is my environment here now. This is actually Elvish. This is probably a shell you might recognize if you've seen it before. And if I look at this BB bin, there's a whole bunch of symlinks that are all very small for different commands. You can kind of see all the stuff that we've implemented here. And there's one BusyBox binary that's 17 megabytes. All right. This should work for any Go code that's pure Go code. We haven't actually dealt with CGo before, and we don't want to. We don't want to take any dependencies on C. And so far, we haven't had to. There's an alternative to this, actually. One of the other things we've done is compile commands on demand. So we include all of the source of the commands you want in the initramfs, and the 4 Go toolchain binaries, Go, GoLink, compile, and asm, and a small command that will automatically figure out where the command that you named it is in the source tree, and run go build, cache that binary, and run it for you. So I could build one of these with the uroot command as well, build source. Oh, no, we're not going to do that. Unfortunately, Elvish kind of messes up my terminal every time. This takes a little bit longer because it has to figure out all of the dependencies of every command and their dependencies, which I believe is done with go tool list JSON. There's like a command for this that lists you all of the dependent files. So it's going to put those all together. It's also going to recompile your Go toolchain for you from the Go root that you specify. So you can specify a different Go root for the uroot command and say, please compile me this other toolchain to put in the initramfs. That's going to take 10 seconds more. When I start this, you're going to notice that we're going to have to wait. The Go compiler has gotten slower over the years, so it takes about 5-10 seconds for init to compile before it runs, and then it takes about 5-10 seconds for the shell to compile before it runs. I'm going to do that again. Now we're waiting for init. And the shell. Come on, the shell is a little bigger. If I look at ubin, now we have to wait for LLS. Sorry. you can see that the only 3 commands that have actually been compiled are elvish, init, and ls. This is actually kind of interesting because if you include a text editor in your initramfs, you can iterate on commands within this environment. Like I could remove ubin ls, edit the ls source, and then type ls again to run it again. It'll get recompiled and cached in that directory. So now the second time around, we're still going to have to wait for ls because it's getting recompiled. But if I don't remove it, you get the cached version immediately. So it's only the first time that you have to wait. All right. So the third major challenge that we had to solve in Go, and I should say, we usually use the BusyBox approach. It's usually way smaller. If at some point we could BusyBox the Go toolchain itself and get one Go toolchain binary in a bunch of source, that might be the smallest we'll ever get. But it doesn't work currently, and there's a bunch of corner cases in BusyBox that you'd have to solve that we haven't had to solve because the normal BusyBox approach is small enough for us at the moment. So the last thing that we've actually had to write is bootloaders in Go. And the first question to answer is, what on earth actually is a bootloader, or what is a loader in general? And it's 2 things at its core, right? It parses an executable binary according to some format. That format is ELF on Linux, it's PE32 on Windows, and PE32 in UEFI. And then you copy parts of that binary, usually like code segments and text segments and all that stuff, to pieces of memory that the ELF executable tells you to copy it to in some table. Right? So it could say, take 400 bytes from the file at offset 100 and put them at 0x400, 100 in memory at that address. Then it might do some fix-ups and some other stuff. It doesn't actually matter all that much. And when you're actually ready and everything's been copied into memory, you jump to an entry point. The binary also should tell you in some table somewhere, hey, this is my entry point. This is where you should jump to start the program. So for example, that could be 0x400, 100 if you copied a bunch of code to that segment. So a bootloader is actually nothing more than that, right? That's how your binaries get loaded on Linux when you run stuff in user space, but the same concept applies to bootloaders. It's just that instead of running it in user space on top of Linux, you're going to replace Linux with the thing that you're loading. So Linux actually has a system call for this. It's called kexec. And you can kexec load a bunch of segments with an entry point. Right, so you specify, here's a bunch of buffers that I want you to copy, and I want you to put them at these physical addresses. And then you say, once you're done with that, please jump to this entry point to start the new kernel. This is, of course, something you can do in Go as well, right? You just redefine the same structures, you figure out how to call the system call. The harder part then is managing the memory around. How do you allocate memory to the right place, and where do you put things and stuff? And one thing that you might think of is like, what if I end up copying over the Linux kernel itself? But actually, you don't have to worry about it because the Linux kernel takes care of it for you. It'll figure out which parts of itself will get copied over, and it'll take a piece of code that does the copying and move it to like a special place outside of everything, and then basically stop itself, jump to this copying code, and like copy over itself. It's pretty cool, but also way too complicated. But all the preparation for this is stuff that we can do in Go, and we actually have. So we ended up writing a multi-bootloader that parses multi-boot kernels, stuff like Zen the hypervisor, VMware ESXi, tboot, some other random things. So these are all things that you can actually boot from Linux now using these commands. There's one more weird thing that we had to do. When you load a program, it usually also expects to be given arguments, right? Your normal C program or your normal program on Linux has an argc and an argv, right? And these are things that are passed in like registers when the program is started. Registers are on the stack when you jump to the entry point. So what if you have to do that for a kernel, right? Some kernels expect the register EAX to contain a pointer to some structure that has to be somewhere. Well, what you have to do, because kexec is too generic for this, is insert another piece of code that you jump to first. It'll set up that structure and then jump to the real kernel's entry point. This is then code that runs between Linux and the new kernel in ring 0. But we didn't want to actually include any like C or like assembler build systems in building uroot. We would like everything to be buildable with Go build. So what we actually did is write a bunch of Go assembly that does this trampoline is what this concept is called, and kind of coax Go into compiling it, but it's not actually code that you can use in the Go program itself. It's code that's meant to be copied into ring 0 at the execution of the bootloader. So there are a bunch of hacks in there, as you might imagine, and you can look at it if you're interested. But at this point, that means we've actually been able to write a full bootloader in Go using the kexec system call. So at the moment, we can load Linux, we can load multi-boot kernels. We're working on some crazy ideas for booting Windows, which some are crazier, some are less crazy, and it's definitely doable. And then there's a bunch of like utilities like grub config parsers and syslinux config parsers, and you can do a PXE netboot with Go from user space, because really it's just DHCP, which you can implement in Go, and some other stuff. So lastly, I'm going to tell you just a little bit about the project. We're here to provide tools for a community, and we like to get other companies involved. We're not going to be too opinionated on the things you should actually use. So if you don't want to use uroot and you want to use something else, that's totally fine with us. There's people that hate Go. They're probably not in this room. But and we develop most of this open source first. It's kind of orthogonal to LinuxBoot, but we're also somewhat pushing for security and user freedom. A lot of laptops that you buy today, you won't be able to change firmware on, even to this, because it has to be signed by Intel or by a firmware vendor. That doesn't afford you any control over your own machine. If you could sign it yourself with your own set of keys, that would actually be ideal. So there's some things in the works there. And the usual model for when things don't verify, I don't know if you've tried to secure boot like Linux or something. The usual model for when it doesn't verify is the machine stops booting. It's a brick, right? I can't verify what I'm about to boot, so I'm just going to not. But that's kind of not acceptable in a data center of like hundreds of thousands of machines, because if all of your machines suddenly turn into bricks and you have to actually go touch them to recover it, that's not a good recovery policy. So we want to have tools for securely booting even if your thing doesn't verify. That might be something like, we'll boot anyway, but you won't get access to these secrets that you need to decrypt the disk, for example. But that's outside of the scope of this talk. And lastly, if you're interested, there is a website, and most actively, there is a Slack channel. which you can find on the website. You can also talk to me on Twitter. We'll definitely try to help you with any hardware that you might want to port. And I brought stickers, but I need to get them from my hotel room. So they'll be out there somewhere later in the day. Thank you very much.